The last time we talked about the Ramsey number or complete graph, KK and KK, which we just write RKK. What about more general graph? What we know is that if H has K vertices, then this H is always a subgraph of this complete graph on K vertices. So this RH, H is always at most RKK, which we saw that this is at most exponential. On the other hand, we show a lower bound, which is also exponential, but it's not clear whether this kind of lower bound applies to more general graph H. Indeed, if we mimic the proof of this lower bound, which we discussed in the introduction to the graph theory course, which also uses the probability method, if we mimic it, then we also be able to obtain a lower bound on the Ramsey number on more general graph H. In fact, if this H, say, is a K vertex graph with, say, K times D edges, then we can find the lower bound as exponential index D. Actually, D is the half of the average degree, which is the number of edges. D is the number of edges in H divided by the number of vertices in H. Proof is essentially same probability method. Let's just take n as 2 to the d minus 1 and consider random 2H coloring of the Kn. Then what? If you have for any vertex set of size K, the probability, we can compute the probability that this K vertex yields a monochromatic copy of H. We can actually compute it. This is at most. So you choose color, either red or blue. And then if you have a K vertices, then there is at most K factorial ways to take a copy of H. For example, if your H is this, then you can either take a copy here, or here, or here, or here, or here. So there are 5 ways. That's 5 because this has lots of automorphism. Changing this 2, this 2, this 2 does not change the graph at all. So there are 4 factorial many graph of automorphism on this graph. So 5 factorial over 4 factorial is 5. In general, it's like a K factorial divided by the number of automorphism on the class under this graph. So this is at most K factorial. And for one specific way to take it, the probability that this all becomes the color that you have chosen is what? 2 to the KD. So 2 to the negative KD. So using the union bound, there are n choose k choices of k set, and each of them has probability and most this to use a monochromatic copy of H, and you can compute that this holds, and from our choice of this n, what this is the most 2 to the 1 minus k, and then k is this is strict, and this is at most 1. So this shows that with positive probability, you can avoid any monochromatic copy of H, so you get this bound. This shows that if this H has quadratically many edges, then it is exponential. The Ramsey number is exponential. And even if it has less than quadratic, if the H has k to the 1 plus epsilon edges, and this already says that this is exponential to the some polynomial. So this is, large. Then what are the graphs with the small Ramsey number? So from this bound, what would be the natural candidates for the graphs with small chromatic number? So here, the average degree is somehow related. So the natural question is that what if we have a graph with constant average degree? Then maybe these have a small Ramsey number. The smallest possible is that in order to find H, of course, you need to have the order of H many vertices. So possible case is that when does this become the constant times the number of vertices H? For which graph H? And this previous proposition suggests that maybe the graphs with constant average degrees are the good candidate. However, this alone is not enough because you could consider k square root of k here. The square root of k vertices, you put all the edges between them. So this is click. And there are k minus square root of k many isolated vertices. Then what's the average degree? So this has k vertices. And what? Square root of k choose 2, which is essentially k over 2 edges. So it has constant average degree. However, in order to find the monochromatic copy of this, you need to find the monochromatic copy of this. So RHH is at least as large as Ramsey number of square root of k and square root of k, and that's at least 2 to the square root of k over 2. So again, this is somewhat exponential. So this condition alone is not enough. But if you see, in this case, the problem was this is essentially a complete graph. All the edges are cluttered here. So this was not really important part. The important part was very dense. So natural question is, what if we have a graph whose edges are quite scattered around? What does this scattered around means? In other words, that does not have a small subgraph with high minimum degree. And we already know such a concept. We have learned in the Introduction to Graph Theory course about such concept in the name of degeneracy. The degeneracy of graph was the, maximum max of the mean degree of or subgraph. Let's write it as H prime subgraph. This kind of suggests that the degeneracy is the right concept to deal with the graph Ramsey number from this example. Actually, so Ball and Erdős in 1975 conjectured that every digit degenerate graph H satisfy RHH of some constant time. This is constant times the number of vertices in H, where this constant C is only depending on the D. So no matter how large H is, no matter how large K is, it doesn't matter. This is recently proved by Chung-Bom Lee in 2017. Okay. So this proof is quite complicated. It uses some sort of dependent random choice to prove it. And we will not talk about that result, but we want to talk about weaker result by Pratar, Roder, Semoradi, and Trotter in 1983 about the more restricted class of graph than degenerate graph. They consider the graph with bounded maximum degree. So let's say delta is some number, and let H be a graph of maximum degree and most delta. Then they show that there exists a constant C which only depends on this delta, such that this Ramsey number is at most C times the number of vertices in H. So how do we prove this? Essentially, how we want to prove it is using the regularity lemma. In regularity lemma, you have a reduced graph, which is constant size. In there, you want to find the, okay, when I say we apply the regularity lemma, we consider a graph G whose edges are colored by red or blue. So you consider red as an edge and blue as a non-edge, then you get one graph. And then you apply regularity lemma. And then you consider the reduced graph, and the reduced graph, you might either find the complete graph on, say, some t number of vertices, or independent set of a t number of vertices. And there, if it's a complete graph on t vertices, that corresponds to the, red edges between this cluster, which are Lipschitz regular. There you apply embedding lemma to embed H. And if you have a independence of size K, then there you consider the blue edges, which is complement of red. And then you apply embedding lemma to apply H. That's the kind of idea. Because we have this embedding lemma, where that if you have a epsilon regular partition, and then the parts here are epsilon regular, then you can pretty much embed as long as they are like as long as this part has h has a bounded maximum degree, then you can embed this h into G with some flexibility. So because the entire the regular theorem give you the number of clusters is constant, so this part is only the constant fraction of the entire graph. So even if h it has a linear size compared to G, we will be able to embed. So regularity lemma kind of reduces the problem into finding clique problem in a constant size graph. So we'll see. I will write the proof in more detail so you will know what I mean. So let's say K with a Ramsey number of K delta plus 1, comma K delta plus 1. So remember this delta is a constant, and then this C is a constant depending on delta. And this is also constant depending on delta. So when we define C, we can we can use K. Then still this is a function depending on delta, which is just the constant. And this be the Ramsey number. So in other words, if you have KK, in KK, no matter how you color the edges with the red or blue, you will be able to find the K delta plus 1. Okay, and let's take epsilon small. Something like this would be enough. The exact expression is not too important. We just take this, and then let's say T is not too small, but not too big. Okay. And let's say you take small t. And what? You take, let C be the 3 times t over epsilon, the large constant. Then what? So this k is chosen from delta. So this is function of delta. Then we choose this epsilon, which is small enough for these two, but still a function of these two, this choice. And this t is again chosen so that the regulatory lemma can be applied with the constant epsilon, so that the number of parts is at most t. So we have this. So we take n to be, say, bigger than c times the number of vertices in H. So here this is like 3 times t over epsilon times the number of vertices in H. What do we want to do? We take 2H coloring of K sub n. And let G be the graph with red edges. So you take a red blue coloring and we apply regularity lemma to G with parameters epsilon and t. Then we obtain a regularity partition, epsilon regular partition, B1 to BR for G, with this R being bigger than equal to T and smaller than equal to T, capital T. And what do you know? Each BI is large. Why? So this is what we know, and then the number of parts is at most t, so this is like at least 2 over epsilon times the number of edges in H. So we consider the epsilon 0 reduced graph R on the vertex set bracket R. And in that case, what do you have? Ij is an H in R if and only if Bi and Bj is epsilon regular. Because here we put 0 means that we don't care about density. It's epsilon d regular, but even if d is 0, it's fine. If they are empty set, still it's fine because they are epsilon 0 reduced 0 regular. So, I mean, if there are no edges at all between Bi and Bj, then Ij is connected in R. Then what do we know? Since this is a epsilon regular partition, we know that epsilon regular partition means that every pair between every Bi and Bj, except a small fraction, are epsilon regular. That means that this is bigger than 1 minus epsilon times R choose 2. So out of R choose 2 pairs, more than 1 minus epsilon fraction of them are actually epsilon regular. And from our choice of epsilon, this is bigger than 1 minus 1 over k minus 1 times R choose 2. And by Turan theorem, we know the Turan number of kk, and that's this one. So this shows that the R contains a copy of kk. Okay, assume you take first k vertices, then that's kk. By changing the index of the cluster if necessary. So now we consider this copy of kk. And we now color the hij of this copy of kk lead if if epsilon regular with the density more than half or equal to half. And otherwise, color is blue. So one thing you can easily check is that if you have an epsilon regular, epsilon d regular graph, and then you take the complement, you change the edge to non-edge, non-edge to edge, then that's epsilon 1 minus d regular graph. So we know that this is epsilon regular graph. This is epsilon regular pair. If density is more than half, then you color it with red. If density is less than half, then you consider blue edges instead. And that's again epsilon regular with density at least half. Then, as this k is the Ramsey number of delta plus 1, comma delta plus 1, there is a monochromatic copy of k delta plus 1 in this kk. Again, by reindexing, we assume that it is the first delta plus 1 number. If it is lead monochromatic, then we let G prime be G on this delta plus 1 vertices. Otherwise, if this is blue, then let G prime be the complement on this delta plus 1 vertex. Then now what? We have V1, V2, dot V delta plus 1. And here, they are epsilon regular with the density at least half. So each of them is epsilon half plus regular. And what we know is that this is like G prime. It's either red monochromatic or blue monochromatic. But H has maximum degree delta. That means it has a delta plus 1 proper coloring. So this is delta plus 1 par type. You can partition them into x1, x2, x delta plus 1 so that the edges are between them. And this is a setup for embedding lemma. We showed that before. We showed that the embedding lemma allowed us to find the copy of H in copy of G as long as each of that is sufficiently smaller than each of these. And then it has boundary maximum degree. So for each ij, we know that if they are different, Bi and Bj is epsilon half plus regular in this G prime. Also, H is delta plus 1 par type. With its partition class has size at most what? The number of vertices in H, which is at most epsilon times the each Bi over 2. That's because of our choice here. So each of these is quite smaller than this. Only epsilon times the size of this divided by 2. Thus, we can apply the remaining lemma that we learned in the regularity lemma section to find a copy of H in this G prime. This gives us a monochromatic copy of H in our two-colored Kn. And it concludes that the Ramsey number of H is at most 3 times T over epsilon, which was the function of delta times the number of vertices in H. And these are function of delta. Okay, so this shows what we want. And if you think about the dependency of this, how large is this C in terms of delta? So epsilon was taken as this. So this is exponential, and then K was the Ramsey number, which is also exponential. So epsilon is exponential in delta. But there is this T. T was what? T should be sufficiently larger than epsilon so that we can apply the regularity lemma. And as we saw before, the length of the relationship or this number of parts in the regularity lemma is tower type relation. So this T has to be something like 2 to the 2 to the 2, and then this length is like polynomial in epsilon, which is exponential in delta. So you have this tower type function with the height exponential, which is ridiculously large number. So this is a conceptually easy proof using regularity lemma, but in terms of this constant, it's a very bad dependency. So we want to, in the next video, we want to use another method. Instead of using this regularity lemma, we want to use another method to find the better constant. And that will be done by using dependent random choice. I mean, at least for the case where our H is bipartite. For non-bipartite, we will not prove it, but we will mention. But anyway, the next time we will use dependent random choice to prove the same statement for bipartite H, but this time this C will be much more reasonable constant that depends on the delta. Okay, then. Thank you for listening. I will see you next time.